see that we can reconstruct member types. Now let's take it one step further. Let's take apart class hierarchies. And class hierarchies, not just as a structure, but also the relationship via the V table so that we can recover the polymorphism and the inheritance relationships. Who is the base class? Who is the child class? What functions were overridden? All of this we can reconstruct dynamically. Let's show the class reconstruction demo. And which one is it? What's that first one say? Okay, and this one? This one? That's phase space. Speed break. And this one? What's it called? Oh, shoot. Which one is it? I can't see. Class view? Thank you. Okay, here we are. Same type of demo as before. We're going to attach to a target program that actually has that we've created for this demo that has some classes, and we're going to send in a packet, and the classes are going to interact. The packet will be interacted with via the classes. So we're going to do the trace from the point of receive. Again, that's done automatically behind the scenes, so we don't have to actually hunt around and do symbol resolution. Okay. And then we're going to start the trace, send in the packet. There's the trace running. We'll go a couple, 500 deep. Okay, now we're going to bring up the class viewer. Here's all the data members and the functions of the class. And look at the source code. And you can see it matches very closely. We have 3 functions, 2 functions, and 3 variables. We can even detect that the first function was virtual. See that? Virtual function 2. Now we're going to do a second test, and then this one will have a second class that derives off the first one, and we can show the inheritance relationship. It's a different packet type, so we'll send it in, do the trace. And the second class is illustrated. They have different members, different locations in memory. And let's look at the code. Class B. And there's the function. Now you see class C we're going to do next. It's going to be derived from A, so we'll see that next. Another test, another packet type, another trace, this time in red. There's the trace running. All right. Now you can see that we detect class 2 derived from class 0. And you can see the virtual function, and there's 3 more functions down there. Let's take a look at the source code. Notice the address of the function there is the same in both the derived class and in the base class. So that is actually an overridden function that was declared virtual. So there's class C. And we see the third function is called func2. And if you look at the base class, you can see that's the virtual void func2. And we covered that because of the same address being used between class 0 and class 2 in our reconstruction. Again, this happened completely automatically. No reliance on disassembly at this point in time to recover these relationships. Okay, let's jump back to the slideshow. Okay, here's some other ideas. I don't have demos for these, but I'll just quickly go through them. We can use hit counts as another way to derive data. Hit counts are kind of cool. Imagine that I want to I cast a spell like 10 times. And then all I got to do then is look for every piece of code that was executed exactly 10 times. Now 10 probably isn't a good number. Pick something odd like 7 and do something 7 times and look for anything that's a quantity of 7. 7, 14, 28. Because they might get called multiple times. And those are functions that just by the virtue they called the same number of times, they probably relate to the behavior I just injected. Now, that's just another dirty little trick we can play. A number of accesses to a piece of data memory would be another kind of count that we could collect in that manner. So sequential set reduction is basically the idea that we can go in and do something once, 7 times, and then go in and put that on a graph, and then go in and do something again maybe 3 times, and then only keep what's hit 3 times, and do that like 3 or 4 times, and we keep reducing until we keep hitting only the same code over and over again. We sequentially reduce the set and remove the noise. That's a pretty easy trick. And I do have a demo reel for that using memory scans. So comparative memory scanning is the idea that maybe I have 101 gold pieces. I scan memory for the value 101, then I lose some gold pieces and I only have 99. I scan all the remaining locations that I collected the first time against the value 99. Only those that match 99 are kept. I do this 3 or 4 times, and now I only have the memory locations that are actually rapidly tracking my value. I could do that with coordinates. I could do that with memory injected via a packet, anything like that. So my example for this is scanning for an X coordinate with World of Warcraft. And that would be what's that one called again? This one? Okay, thanks. You guys are helping me out a lot. Thanks a lot. There we go. Okay, now I didn't actually write a demo for this. I just used a program called ArtMoney. So if you want to go get this, download it off the net. ArtMoney is really, really good for this particular kind of scan. I'm going to scan for a 4-byte float in memory. I know my X coordinate already, and the reason I know that is I'm in Ollie debug over at World of Warcraft right now. You can drag that over, and I know exactly the offset from the PC structure. There's my X coordinate. The reason I'm scanning is because whenever I change my X coordinate in memory, I get instantly disconnected from the server. They fixed telehacking. So I've been trying to figure out where the actual integrity check is occurring that disconnects me. And so what I want to do is figure out all the locations in memory that are tracking my X coordinate, because I'm figuring one of those might be the backup value that's being compared against my current value to determine whether or not I should be disconnected. So I scan memory for every value that matches my current X coordinate. Those all appear on the left-hand side. Now every scan from here on out is simply going to reduce the set. And so that's hard to see, but there's my character. I'm just going to move the character slightly. The gamma is really messed up on that. Oh well. So it's just somebody moving on the screen. And then the new X coordinate is set. And I will do a comparative scan now and reduce the set by anything that doesn't match that. Okay. Gremlin's back there. Okay. And then put in the new value and do the scan. It's pretty straightforward. And a couple of these entries on the list will disappear because they're not tracking. So you can see how this works. You just keep doing this over and over again. This worked on a ton of games. In fact, ArtMoney is designed for game hacking, even though it could be applied to pretty much any piece of software. Okay, so that comparative memory scanning. Okay, density analysis. I'm going to go really rapidly through all this. The idea is that you can actually learn a lot about the behavior of functions based upon the number of types of particular operations occurring within the control flow. So an example, scan for FPU instructions. If you find a large number of FPU instructions, you're probably dealing with a rendering code or perhaps an encryption routine. So you could take a section of the graph and do a density analysis scan with a threshold meter, and you could tag locations that have a high density of a particular kind of operation. Another thing you could scan for is exits and throws. Exits from the function, got a lot of those, or maybe a lot of throws. You're probably dealing with a parser that's doing a lot of checks of various errors that might be in the packet or whatever it is you're looking at. So that could help you with the parsing. Accesses to a particular range of memory. If you see a whole bunch of accesses to the beginning of a particular buffer, those accesses are probably in some sort of handling function that's not actually doing any parsing. Whereas if you see a whole lot of accesses to the inside of the tracked buffer, you're probably dealing with the parser at that point. So you can differentiate those two classes of packet handlers using the memory range density analysis. You can also look for particular values in memory, like I was alluding to before, like, for example, the amount of gold you have. Branch density could tell you how the relative complexity of a particular function. A lot of branches, probably related to switches, maybe some sort of parsing function again. That's a good example. And number of times a particular function is executed. So high density hit counts are going to be in loops. So if you're looking for copy operations, for example, a high density loop count would be something you would want to start with. Okay, so density analysis can help you in the situation where your graph has a whole lot of information that's shared between two behaviors, and it does happen. I don't know if you saw that earlier, but the flash heal and the regular heal spell looked almost the same. They shared most of the same functions. So there's different kinds of things with density you could do to help kind of mine out of that data the individual things you're looking for. And so the idea is to have a threshold. And this is just a mock-up, obviously. But let's say that I have an arithmetic density, and I want to calculate on floating point geometry, and I drag the slider up and down until I get just maybe 1 or 2 hits. I loosen it up, more appears, I tighten it down, and just, we get 1 or 2 hits. And those would probably be related to the pathfinding code that I was looking for in this example. So in this, perhaps we're looking only for arctangent operations. And arctangent is definitely used when we calculate distance between objects. So that might be part of the World of Warcraft pathfinding algorithm. Loop count, again, really close to all parsers. Parsers, I keep going back to parsers because that's the place you want to look if you're doing exploitation analysis, which is another big area that HB area works in. So we do a lot of work around the parsers. Now, parsers can also help us find very unique code that's specific to a particular program. So a use case you might want to pursue with this is automatically generate NID signatures. And this is going back to incident response again. So you search for some sort of program logic that's unique, typically unique to a program. And loop density happens to be one of those things. So you find the loops, you go and convert all the code bytes in those loops, you unroll them, and you pull out all the common instructions like XOR EAX and all those other ones. And you keep the ones that are unique, particular arithmetic operations. And you create a set of candidate NIDS values that you can perhaps use with Snort. And so here's kind of a screenshot of what I mean. Here's the unroll loop. We mask out common instructions and then create expressions that represent a bunch of candidates that could be NID signatures we could use, and illustrate those on the graph. And then, of course, the team would have to actually go test those to make sure they actually could work. But this might be a rapid way to at least get a bunch of candidate NID signatures the same day that you get the malware and you've captured it. And so this is a really exciting use case that I really want to work on more. I'm going to skip automated flow resolutions. I'm going to go right through this. Sorry, I don't have time to go through it. I have a lot of animated slides for this. Okay. So you'll have to just forgive me as I go through all this. It looks really complicated because it is. I can show you what that is later. In a nutshell, we automatically determine the inputs required, so we don't do fuzzing anymore. We actually calculate the inputs that are required to uncover new control flows because we have all the data flow tracing. What you saw as I was quickly going through is how the algorithm works. But suffice it to say, we create a polynomial that can be used to calculate what the input should have been based on all the branching and control flow. It doesn't work all the time. If you're calculating a branch based upon an MD5 hash, obviously that's not a reversible type of operation, but the basics are that about 80% or more of the operations are very simple to reverse, and so we just put the proper values of the proper offsets instead of guessing and using random, and that covers more control flow. This screenshot was from almost 2 years ago where we actually used it on a target and found a vulnerability. That red line is a stir copy that actually, or a strn copy that where the user can control the length value that's being passed in at the argument. So that's an illustration of how we could use that capability. I'll cover that later if you really are interested in it. I've only got 5 minutes, I think, so I really want to cover phase space analysis. How much? 15? Oh, okay. Well, we'll go back to the other one if I have a little time. Phase space analysis is really, really neat. What I'm going to show you is a three-dimensional graph. It's rendered in OpenGL. And what I've got is I've got breakpoints on the entry of every single function, and I'm collecting a series of all the functions as they run. So I'm getting this number series. Now, the way that phase space works